This video was produced in cooperation with the ESD Association. Our thanks to Stephen Halperin and Associates for technical assistance in the development of this program. Electricity has often been used by brilliant scientists in their experiments. But left uncontrolled, the effects can be shocking. ESD, the sudden transfer of electrostatic charge from one object to another. With lightning, each flash is an immense discharge of static electricity, from a thundercloud where it is built up into the earth below. Think about the crackling and sparks that occur when you remove clothes from a dryer. How about the shock you sometimes feel when you walk across a carpet and touch a doorknob? These examples of ESD, which we can see and feel, last for a fraction of a second and contain anywhere from about 2,000 volts, the lowest level most people can feel, to over 25,000 volts. However, below 2,000 volts there is still enough static electricity to cause static discharge and damage electronic circuits even when we don't feel it. Still, we're generating static electricity all the time. And a lot of common objects around us can be sources of static electricity too. In fact, for some devices, static zaps under 20 volts are capable of damaging or destroying the sensitive electronic components we handle every day. That transfer of static electricity, whether visible or not, is called electrostatic discharge, or ESD. This video is about controlling static electricity to prevent ESD damage. You'll be introduced to ESD and see how it affects the world of electronics and electronics assembly. Then we'll take a look at how ESD can be controlled in a manufacturing facility, both in the work area and during the handling, storing, and transporting of ESD-sensitive devices. So we can better understand what we're dealing with, let's examine the basic physics of static electricity, the primary cause of ESD. Electrostatic charge is created by contact and separation of materials. This phenomenon is known as triboelectric charging. It involves the transfer of electrons between materials. The resulting charge on a material may be positive, negative, or neutral. If one examines the smallest particle of a material, the atom, one sees that protons are positive and reside inside the atom's nucleus. Electrons are negative and orbit at high speed around the outside of the nucleus. When any two materials are placed in direct contact and then are separated, negatively charged electrons are stripped from the surface of one material and transferred to the surface of the other material. Now, both materials are charged with static electricity. Which material loses electrons and which gains electrons will depend on the nature of the two materials. The material that loses electrons becomes positively charged because of the absence of negatively charged electrons, while the material that gains electrons is negatively charged due to the abundance of negatively charged electrons. An atom is neutral when there are an equal number of protons and electrons. When there is an imbalance of electrons on the surface of a material, an electrostatic charge exists. The symptom of a static charge is an electrostatic field. This field can be measured and can influence other objects in the near vicinity. Whenever two materials such as nylon and polyester are brought into contact with each other and are then separated, the two materials become charged. The charge is evident in that it may cause the hair on your arm to stand up. When two corks are similarly charged, the corks will have the same polarity and repel each other. On the other hand, when one cork is charged negatively by the nylon and the other cork is charged positively by polyester, the corks will attract each other. In other words, we can see that like charges repel while opposite charges attract. These charges are referred to as static or static electricity. The word static means at rest, So we can say the electrostatic charge is just sitting on an item, waiting for an opportunity to move or discharge. Thus, ESD is the discharge of a charged object or material. When two conductive objects with different levels of charge come close together or in contact with one another, the charge rapidly moves from one object to the other. This rapid movement of the electrical charge changes it from static electricity to ESD. It is important to understand how certain materials behave with these electrostatic charges. We'll separate them into two categories: conductors and insulators. Conductors are typically some type of metal, like a piece of wire. The term conductor means that this material will conduct electricity. It will freely allow the movement of electrons across the surface or through it. This will enable us to use grounding techniques to eliminate charges. Grounding means providing a path for the charges to flow into the earth, leaving the material in an uncharged state. There are other materials that are also conductors but have a higher resistance to the flow of electricity, meaning they are not very good conductors. The human body and static dissipative materials are examples of these types of conductors. They will allow grounding techniques to be used, but electrical charges are drained slowly. This is actually a desired feature in many cases, since draining charges slowly minimizes the chance of damaging electronic components. The second material is called an insulator. Insulators prevent the flow of electricity. As with conductors, these materials can also become charged, but grounding techniques will have little to no effect on charge neutralization. The last topic in this introductory section relates to the three failure models that were developed to characterize and determine the ESD sensitivity of a device. These are the human body model, or HBM, the machine model, or MM, and the charged device model, or CDM. The human body model refers to ESD damage to a component from the body of a charged person. The machine model refers to ESD damage to a component from a charged conductive object, such as a metallic tool or an ungrounded fixture. For charged device model to occur, a charged device discharges to ground or to a conductor that has a different electrical potential. An example of the charged device model would be ESD damage to a component that gets charged sliding down a feeder in an automatic insertion machine and then contacts an insertion head or another conductive surface. People are a major potential source of ESD. That's because our bodies easily accumulate static electricity. In fact, our bodies can store relatively large amounts of this electrical charge. Doorknobs probably don't mind the spark, but when ESD passes through an electronic device, such as an integrated circuit, it can cause serious internal damage to that component, resulting in a scrapped component. The tiny circuit paths in these sensitive devices can be burned up or severed by an ESD voltage so small that our sense of touch can't even detect it. Remember, we can only feel discharges above about 2000 volts. But some ESD-sensitive components can be damaged by voltages less than 20 volts. And you won't even know the damage has occurred, but the destruction will exist inside the component. Even when the device is soldered onto a printed circuit board, it's still not safe. It can be damaged by a discharge that passes through the board's conductive traces to the ESD-sensitive component. The amount of voltage needed to damage or destroy varies from component to component, but as these devices become smaller and more complex, their sensitivity to ESD generally increases. Sometimes the damage caused by ESD doesn't mean the component will immediately fail. Instead, the assembly passes inspection, gets shipped to a customer, and then fails later on, creating a very unhappy customer. ESD is one of the most serious problems facing the electronics industry today. If it isn't controlled, the results are higher costs, lower product quality, and angry customers, especially if a product fails at a critical time. On the other hand, Controlling ESD means product quality can be improved and costs can be kept down. This usually leads to increased customer satisfaction and sales, which is a win-win situation for everyone. Now that we know what ESD is and what it can do to the electronic devices we handle, let's look at how ESD can be controlled in the work area. The most important thing we can learn about ESD control is that we are the most important part of ESD control. Although not every company has the same exact approach to ESD control, the major ESD standards state that ESD protected areas must have clearly identified boundaries, and that training of personnel who handle ESD-sensitive devices is required. This involves management putting up signs identifying ESD-protected areas and making sure that ESD-sensitive devices are properly labeled. In addition, engineering may control humidity, use air ionizers, and install static control flooring and work surfaces. But none of these methods of ESD control really work without the complete participation and cooperation of every employee. So, since we are one of the main culprits in the destruction of ESD-sensitive devices, let's begin by taking a look at what equipment is available to reduce the risk of ESD damage from people. The idea is to drain off charges in a controlled manner before they reach the devices. To do that, our bodies need to be connected to ground. If a charged ESD-sensitive device comes into contact with a static dissipative surface, this contact safely channels the charge away from the ESD-sensitive devices and drains them into the earth or ground. There are several methods used to drain off charges that we might carry into an ESD-safe area, or that we may generate while doing our jobs. The most common are the wrist strap and the shoe grounder. We'll take a look at the wrist strap first. Wrist straps are very effective for any operation where people are seated at their workstations. They're also effective for standing operations that don't require much movement. Shoe grounders are not as effective when seated because people may raise their feet and lose contact with the static control flooring. The wrist strap needs to be worn snugly against bare skin. It should be attached securely to a ground wire with a current limiting resistor and some form of quick connect disconnect. The current limiting resistor in the wrist strap cord limits the current flow through this intentional path to ground if the wearer comes into contact with sources of live power. Wrist straps should be tested at regular intervals to make sure they are working properly. Your company will let you know where and how often you should do this. When testing the wrist strap, plug the cord into the wrist strap tester and press the test button. Shake your wrist and stretch the cord to check for intermittent failures. This test confirms continuity between the wrist cord, the wrist strap, and the proper connection to your body. A fail indication means that one or more parts of the wrist strap system are faulty. If you experience any problem with your wrist strap, let your supervisor know immediately. Standing operations involve foot and floor ESD protective systems. We'll look at flooring first. Many facilities have ESD protected areas that contain static control flooring, which includes grounded floor mats. These types of products minimize static charge generation and drain static electricity to ground from people wearing shoe grounders. Static control flooring may be conductive or static dissipative. Some facilities do not have ESD protected areas with static control flooring installed. Shoe grounders will not work without static control flooring. What exactly are shoe grounders and how do they work? Shoe grounders